We're asked for parametric equations for the line of intersection of two planes and the angle between the planes. The planes are x plus y plus z is equal to 1, and x plus 2y plus 2z is equal to 1. I'm going to use some colors here. This is kind of tough to conceptualize, but once you get it, you get it. As visuals for this, let's go ahead and just visualize two planes. I've drawn here two planes that intersect kind of in an X because it's the easiest way for me to draw it. And here's their line of intersection. Now that line of intersection has a direction vector. If I knew the direction vector and then if I knew a point on both planes, then we'd be in business. Let's work on finding that direction vector. Each of these planes has a normal vector. Call this one n1 for the blue plane. It's orthogonal to the surface. And n1 has components 1, 1, 1 from the equation of that plane. The other plane has a normal vector as well. Call it n2. It's orthogonal. And n2 has components 1, 2, 2, again, from the equation of that plane. Now I want you to look at the picture here and think for a minute, how am I going to come up with a vector that is parallel to the line L? And if you're struggling with that, I want you to pause actually and think about it for a little bit. I'm going to move on. Are you ready? Are you ready? Here we go. Folks, if we form the cross product of n1 and n2, then we're going to get a vector v that's orthogonal to both of them. And because each vector is independently perpendicular to its own plane, each of those vectors is also perpendicular to the line L. Therefore, the direction vector for the line is given by the cross product of n1 cross n2. You can confirm, do it ahead if you want, and like pause the video and work it out, but you can confirm that the vector v is going to have components 0, negative 1, 1. So that was actually probably the easy part, coming up with the direction for the line. Now we need a point on the line. Well, for the point on the line, we have a system of equations, essentially, these two equations of the plane. And so we need to use some algebraic techniques here. If I take x plus y plus z equals 1 and subtract from it the second equation of the plane, so I have negative x minus 2y minus 2z is equal to negative 1. Then I end up with negative y minus z is equal to 0. Well, that implies that y is equal to negative z. So whatever y is, z is the negative of it. So if we let y equal 0, then that means that z is also equal to 0. What about x? Well, we eliminated x from the equation, so instead of eliminating x, let's go another way with this. Let's take the first plane's equation, multiply it by 2, so we get 2x plus 2y plus 2z is equal to 2. And then take this equation as is, the one where we multiplied by negative 1 for the second plane, negative x minus 2y minus 2z is equal to negative 1. If we add those two equations together, then we get that x is equal to 1. Therefore, we can use the point 1, 0, 0 together with our vector 0, negative 1, 1. We wanted parametric equations for the line of intersection, and so x is going to equal 1, y equals negative t, and z equals, well, 0 plus 1t, so t. Those are our parametric equations. Folks, I should point out here that when we let y equal 0 so that z was 0, that was an arbitrary choice. And then remember, for the symmetric equations, these are parametric equations, we're using x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct with the point 1, 0, 0 and the vector 0, negative 1, 1. So that takes care of part A. Part B is the angle between the planes. Well, folks, the angle between the planes is going to be the same as the angle between the two vectors, the normal vectors. And recall that the cosine of theta between two vectors is going to be, in this context, n1 dot n2 divided by the magnitude of n1 times the magnitude of n2. Our vectors were 1, 1, 1 and 1, 2, 2. So n1 dot n2 is equal to 1, 1, 1 dotted with 1, 2, 2. That result's going to be 1 plus 2 is 5. The magnitude of n1 is equal to the square root of 3. The magnitude of n2 is equal to 3. So we have that the cosine of theta is equal to 5 divided by 3 root 3. And using a calculator, we get that theta is approximately 16 degrees.